Hello there, and welcome to Sleepy Science. Every moment of your life is controlled by something you can't see, touch, or stop, and yet it never pauses for anyone. Time quietly moves forward whether we notice it or not. But here's the strange part. Scientists have discovered that time doesn't actually pass the same way everywhere. In some places in the universe, it can move slower, and in others, it can move faster. Even your own brain can stretch or compress how long a moment feels. So tonight, we're going to slowly explore some of the most relaxing and fascinating facts about time, and by the end, you might start experiencing it a little differently. When people say time is passing, they usually mean something very simple. They mean that events are moving from one moment to the next. A moment happens, then it becomes a memory and a new moment replaces it. Think about your day. In the morning, you wake up. Later, you eat lunch. After that, evening arrives. Each event follows the one before it, and that steady change is what we call time passing. But here is the interesting question. Is time actually moving, or are we the ones moving through it? Scientists often say that time is a way to measure change. When something changes, we notice time. When nothing seems to change, time feels slow and quiet. This is why a boring wait can feel very long, yet a busy day can feel short. So when people say time is passing, they are really noticing one simple thing. The world around them keeps changing, moment by moment, and their mind keeps recording those changes as a sequence of events. Now think about how humans experience time. Most people feel that time moves in one clear direction. It starts in the past, moves through the present, and continues into the future. You remember yesterday, you live in today, and you imagine tomorrow. This direction feels natural, almost like a river flowing forward. But the reason we experience time this way is closely connected to memory. Your brain can store memories of things that already happened. You remember a meal you ate, a place you visited, or a conversation you had. But you cannot remember something that has not happened yet. The future is unknown, so the brain treats it differently. Because of this, the mind organizes life in a simple order. Past events behind you, present events happening now, and future events still ahead. This way of organizing experiences helps humans make decisions and plan actions. It also explains why time feels like it is moving forward, even though the deeper nature of time is still a mystery. Another interesting thing about time is that it usually feels steady and constant. A minute on a clock always contains 60 seconds. An hour always contains 60 minutes. Clocks measure time with very precise systems, so the numbers stay the same everywhere. But the human mind does not always feel time in the same steady way. Sometimes an hour feels short, and other times the same hour feels long. This happens because the brain does not measure time like a machine. Instead, it estimates time based on attention, emotion, and activity. When your mind is busy with many things, the brain pays less attention to the passing minutes. Because of that, time feels faster. But when you are waiting or bored, your brain notices every small moment. That extra attention stretches the feeling of time. So even though clocks measure time in a constant way, the experience of time inside the mind can change from moment to moment. Many people notice something strange about growing older. When you are a child, 1 year can feel very long. Waiting for a birthday or a holiday can seem endless. But as people become adults, years often feel like they move much faster. There is a simple reason for this difference. When you are young, almost everything is new. You experience new places, new skills, new friends, and new discoveries. Because the brain is processing many fresh experiences, it stores more detailed memories. Later, when you look back, that year appears full and long. As adults grow older, life often becomes more routine. People wake up, go to work, follow similar schedules, and repeat many activities. When fewer new experiences happen, the brain stores fewer unique memories. When you look back on that time, it feels shorter because there are fewer distinct moments remembered. So childhood years feel longer not because time actually slows down, but because the brain records those years in richer detail. Think for a moment about how attention works in your daily life. When your mind focuses closely on something interesting, the outside world often fades away. You might read a story, watch a film, or work on a task, and suddenly notice that an hour has passed. But it did not feel like an hour at all. The reason is simple. Your brain only has limited attention, and when that attention is fully focused, it stops checking the passing seconds. Scientists explain that the brain usually notices time by observing small changes around us. But when attention is deeply occupied, the brain stops monitoring those changes. Because of that, fewer signals about time reach your awareness. Later, when you look at the clock, you feel surprised. It seems like time moved quickly, even though the clock moved normally. This shows something very interesting. The more your mind concentrates on something meaningful, the less it notices the passing of time itself. Now imagine a different situation. You are waiting for something important, maybe a message, a ride, or the start of an event. During waiting, something strange happens inside the mind. The brain has little to do, so it begins to notice every small moment. Instead of focusing on activity, attention moves toward the clock, the environment, and the feeling of waiting itself. Because the brain keeps checking time again and again, each minute becomes very noticeable. You may look at the clock, then look again, only to see that very little time has passed. This repeated checking stretches the feeling of time. Psychologists explain that boredom and waiting increase awareness of each second. When the brain has nothing interesting to process, it measures time more closely. That is why a short wait can feel surprisingly long. The clock is moving normally, but your attention is measuring every tiny step, making time appear much slower than it really is. Now think about the opposite situation. You are enjoying something you love. Maybe you are talking with friends, playing a game, or exploring a new place. During these moments, people often say the same thing. They say time flew by. The reason is closely connected to how attention works again. When you are enjoying an activity, your brain becomes busy processing sights, sounds, and ideas. Instead of counting seconds, it focuses on the experience itself. Because the mind is fully engaged, it does not keep checking the passing time. The brain is simply too occupied with the activity. Later, when the moment ends and you look at the clock, you feel surprised at how quickly the time seemed to move. The clock did not change its speed at all, but your brain paid less attention to the passing minutes. This shows that enjoyment changes the way we experience time, making even long periods feel short and effortless. For a long time, people imagined that the brain might contain a single internal clock, something that measures time the same way a watch does. But modern research shows that the brain works very differently. Instead of one clock, the brain uses many systems to estimate time. Different parts of the brain handle different types of timing. Some systems help measure short moments, like the time between sounds or movements. Other systems help track longer periods, like hours or days. Scientists discovered that these systems work together rather than relying on one single timer. This explains why our sense of time can change depending on what we are doing. Attention, emotion, movement, and memory all influence different timing systems in the brain. Because many systems are involved, our experience of time can stretch, shrink, or feel completely different in different situations. In other words, the brain measures time using a network of processes instead of one simple clock. Think about how your brain handles different kinds of time. The time needed to blink is very short. The time needed to cook dinner is much longer, yet your brain can estimate both. Scientists discovered that the brain uses several systems instead of one single timer. One group of brain cells helps measure very short moments, like fractions of a second. These help you speak clearly, move your hands, and react quickly. Another system works with longer periods, like minutes or hours. This system helps you plan activities, finish tasks, and follow schedules. These systems communicate with each other, sharing information about events and changes around you. Because of this teamwork, humans can sense time across many different scales. You can notice a quick sound and also understand how long your day has been. This shows something important. The brain does not depend on one clock. Instead, it uses a network of systems, each helping estimate time in its own way. Now consider something surprising. The way you remember events can change how long those events seem to last. Memory plays a large role in how humans judge time. When the brain stores many details about an event, the mind later feels that the event lasted longer. But when only a few details are stored, the event may seem shorter in memory. Imagine a busy day full of activities. You visit places, talk with people, and notice many new things. Later, when you think back on that day, it feels rich and extended because your brain saved many memories. Now imagine a quiet day with very little happening. When you look back, it feels short and simple because fewer memories were recorded. The brain uses memories almost like markers along a path. The more markers you have, the longer the journey seems when you remember it. So memory quietly shapes how long past moments appear in your mind. Now think about the last time you tried something completely new. Maybe you traveled to a new city, started learning a skill, or explored a place you had never seen before. During these kinds of experiences, many people notice something interesting. The day feels full and long. The reason comes from how the brain processes new information. When something is unfamiliar, the brain becomes very alert. It pays attention to details, sounds, shapes, and movements. Because everything is new, the brain records more information than usual. Each new detail becomes a memory. Later, when you remember that day, your mind sees many different moments stored closely together. This makes the day appear longer when you look back on it. In simple words, new experiences stretch the feeling of time because the brain records more information. The more new things your mind processes, the more detailed the memory becomes, and the longer that period seems in your mind. Now imagine the opposite situation. Many parts of daily life follow the same pattern again and again. You wake up, prepare for the day, travel to work, complete tasks, and return home. When activities repeat often, the brain becomes very efficient. It no longer needs to pay close attention to every small detail. Instead, it begins to process these actions automatically. Because the brain is not recording as many new details, fewer memories are stored during these routine periods. Later, when you think back on the week or month, the time feels shorter because fewer distinct moments stand out. The brain remembers only the general pattern instead of many separate events. This creates the feeling that time moved quickly. The clock did not change speed, but your brain saved fewer markers in memory. So routine activities compress the feeling of time, making long stretches of life appear shorter when remembered. Think about the last time you traveled somewhere new, maybe another city or another country. Many people notice something interesting during travel. One single day can feel very full, almost like several normal days combined. The reason comes from how the brain reacts to new environments. When you enter an unfamiliar place, your mind becomes very alert. It notices streets, buildings, sounds, languages, and faces that it has never seen before. Because everything is new, the brain pays closer attention and records more information. Each small discovery becomes a separate memory. Later, when you think about that day, your mind finds many detailed moments stored in memory. Because there are so many recorded experiences, the day feels longer and richer. Scientists explain that travel increases the number of new signals the brain processes. This increases memory formation, which stretches the feeling of time when you remember the day afterward. Now imagine a very different situation. You are sitting somewhere with nothing interesting to do. Maybe you are waiting in a long line, or sitting quietly in a room with no activity. During these moments, people often feel that time is moving very slowly. A few minutes can begin to feel much longer. The reason again involves attention. When the brain has no engaging task, it starts focusing on the passing time itself. Instead of being busy with activities, your mind becomes aware of every small moment. You might check the clock, look around, and feel the seconds moving slowly. Because your attention keeps returning to the idea of waiting, each minute becomes very noticeable. Psychologists explain that boredom increases awareness of time. The brain measures each second more carefully, making the experience feel stretched. So even though the clock continues normally, your awareness of time becomes stronger, and that makes short periods feel unusually long. Inside the brain, time is not measured by a single center. Instead, scientists discovered a group of connected systems that help estimate time in different situations. These systems are often called internal timing networks. They include several brain regions that communicate with each other while we move, think, and observe the world. Some parts help measure short intervals, like the timing needed to catch a ball or speak clearly. Other parts help track longer periods, like planning a task or estimating how long an activity might take. These systems share information constantly. When you walk, talk, listen, or make decisions, the timing networks help coordinate your actions. Without them, everyday activities would become confusing and unorganized. This shows something important about the brain. Our sense of time does not come from one small area. Instead, it comes from a group of connected systems working together, quietly helping us understand how moments unfold. Another interesting factor that changes our sense of time is a chemical inside the brain called dopamine. Dopamine acts as a messenger between brain cells and plays an important role in motivation, reward, and attention. But scientists also discovered that it affects how we experience time. When dopamine levels change, the brain's timing systems can behave differently. Higher dopamine activity often makes people feel more alert and focused. In this state, the brain processes information quickly, and time can seem to move faster. Lower dopamine activity can have the opposite effect, making the mind feel slower and less engaged. In that state, time may appear to stretch. Researchers observed this effect while studying movement, learning, and decision-making. Because dopamine influences attention and brain activity, it also shapes how we estimate time. So the feeling of time passing is not only about clocks or events. It is also connected to the chemical signals moving through the brain. Now think about how emotions affect your sense of time. A moment filled with strong feeling often seems different from a normal moment. When people feel excitement, anger, sadness, or surprise, their brain becomes more active. The mind starts paying closer attention to what is happening. Because of this extra attention, the brain records more details during that short period. Later, when you remember that moment, it may seem longer than it really was. For example, a surprising event might last only a few seconds, yet it feels extended when you recall it. Scientists explain that emotions increase awareness and memory activity in the brain. The mind becomes alert and focused on the event. This causes seconds to feel stretched while the experience is happening. So emotions can quietly change the way time feels, even though the clock continues moving at the same steady pace in the background. Now imagine a moment of sudden fear. Perhaps a loud noise happens or something unexpected moves near you. During that brief moment, many people report the same strange feeling. Time seems to slow down. A few seconds can feel much longer. This effect happens because fear activates a strong survival response inside the brain. The brain quickly becomes extremely alert. It begins scanning the environment for danger and possible actions. Because the brain processes information more rapidly, it records many details within a short time. Your mind notices small movements, sounds, and changes that might normally pass unnoticed. Later, when you remember the event, the moment feels stretched because so many details were captured. Scientists believe that fear does not actually slow time itself. Instead, it increases the speed of brain processing. More information is recorded during those seconds, which makes the experience feel longer when remembered. Now consider another situation. You are deeply focused on a task that requires full attention. Maybe you are solving a problem, building something, or working on a creative idea. During these moments, people often notice something surprising. Hours can pass without being noticed. When you finally look at the clock, you feel amazed that so much time has gone by. This happens because intense focus uses most of the brain's attention. When the mind is fully engaged with one activity, it stops monitoring the passing minutes. The brain becomes occupied with processing ideas, movements, and decisions connected to the task. Because attention is directed toward the activity, instead of the clock, time awareness becomes weaker. Psychologists sometimes describe this state as deep concentration. In this state, the brain becomes efficient and highly engaged. As a result, long periods can seem very short, simply because the mind is not watching time as closely. Now think about what happens when you sleep at night. During sleep, your brain enters a very different state from waking life. Your body rests, and many mental processes slow down. But important activity still continues inside the brain. While you sleep, the brain organizes memories, restores energy, and adjusts many internal systems. One of the changes involves your perception of time. When you wake up in the morning, your mind often feels refreshed and ready to begin a new day. The brain has reset many of the signals that affect attention, mood, and awareness. Because of this reset, your sense of time becomes balanced again. Waiting, focusing, and remembering may feel different compared to the night before. Scientists explain that sleep helps restore normal brain activity and chemical levels. This quiet process helps the mind measure time more clearly when you wake up and begin another day. Inside your body, there is a quiet system, working all the time, helping guide when you feel awake and when you feel sleepy. Scientists call this system the circadian rhythm. The name may sound complex, but the idea is simple. It is the natural daily cycle that controls many activities in the body. This rhythm influences sleep, energy levels, body temperature, and even hunger. Long before alarm clocks existed, humans and animals were already following this internal schedule. The brain receives signals from the environment, especially light and darkness, and uses those signals to guide daily patterns. Because of this rhythm, many people feel alert during the day and relaxed as night approaches. The circadian rhythm works quietly in the background, helping the body prepare for different parts of the day. So when you start feeling naturally sleepy in the evening, it is not random. Your internal rhythm is guiding your body toward rest. Now here is something fascinating. Your body can actually keep track of time without looking at a clock. Inside the brain, a small group of cells works like a natural timekeeper. This system helps the body follow a cycle that lasts close to 24 hours. Scientists discovered that even when people stay in places without windows or clocks, their bodies still follow a daily pattern. They wake up, feel hungry, become tired, and fall asleep at roughly regular times. This happens because the brain's internal clock continues running on its own. The cycle is not exactly perfect. In many people, it lasts a little longer than 24 hours. That is why the body needs small adjustments from the outside world. But even without those signals, the brain still tries to keep the day organized. This shows that humans are naturally built to follow a daily rhythm that repeats again and again. Now think about what happens when morning sunlight reaches your eyes. Even if you are not paying attention, that light sends an important signal to the brain. Special cells in the eyes detect brightness and send information to the brain's internal clock. When the brain receives this signal, it adjusts the body's daily rhythm. This process helps keep the body's schedule aligned with the natural day outside. Without sunlight, the internal clock might slowly shift later and later, but morning light gently pushes the cycle back into balance. This is why exposure to daylight can make people feel more awake and alert during the day. It tells the brain that a new day has begun. Over time, the brain learns to expect this signal every morning. In this way, sunlight acts like a daily reset for the body's internal timing system, helping it stay connected to the natural cycle of day and night. Now consider something you may have noticed many times. Even if you do not check a clock, you often begin to feel sleepy when night arrives. This happens because the body is following its internal rhythm. As evening approaches, the brain slowly prepares the body for rest. One important change involves a chemical signal called melatonin. When darkness increases, the brain releases this signal to tell the body that night has arrived. At the same time, body temperature drops slightly, and energy levels begin to decrease. These changes create the calm feeling that encourages sleep. This process works even if you are not watching the time. The brain already knows roughly when night should begin. That is why many people start feeling relaxed and tired around the same hours each evening. The internal clock has been quietly counting the day, guiding the body towards sleep when the right moment arrives. Think about the last time you traveled across multiple time zones, maybe on a plane far from home. You probably noticed something strange. Your body felt tired at odd times, awake when it should be asleep, and hungry at unusual hours. This is called jet lag, and it happens because the body's internal clock is still set to the original time zone. Your brain and organs continue following the old rhythm, while the new environment has a completely different day-night cycle. Light, meal times, and social cues in the new location signal one schedule, but your internal clock signals another. The result is confusion, fatigue, and difficulty sleeping. Scientists explain that it takes several days for the circadian rhythm to adjust to a new time zone. During that adjustment, the body is temporarily out of sync with the environment. Jet lag shows how powerful and precise the internal clock is, and also how sensitive it is to changes in the external world. Inside the brain, there is a chemical signal called melatonin, which plays a critical role in telling the body when it is time to sleep. As evening approaches, the eyes detect fading light and send this information to the brain. In response, the brain begins releasing melatonin, which spreads through the body and encourages feelings of calm and drowsiness. This signal prepares the body for rest, slowing down alertness and reducing energy. Scientists describe melatonin as a natural bedtime cue. It works quietly, helping guide the body from wakefulness into sleep without conscious effort. Even if someone ignores the time or is distracted by activity, melatonin gradually increases and encourages sleep. Exposure to bright lights or screens can delay melatonin release, which is why staying on devices late at night can make it harder to fall asleep. Overall, melatonin is a key signal that the brain uses to know when nighttime has arrived and when the body should prepare for rest. Another interesting fact about the body is that temperature also follows a daily pattern. During the day, your body temperature is usually higher, helping you feel awake and alert. This increase supports physical activity, mental focus, and energy. In the evening, as darkness approaches, body temperature gradually drops. This cooling is part of the process that signals the body it is time to relax and sleep. Scientists explain that this natural temperature cycle is closely connected to the internal clock. Even small changes in temperature can influence feelings of sleepiness and alertness. When the temperature drops, the brain interprets it as a sign that night is coming, encouraging calm and rest. The temperature cycle repeats daily, supporting the rhythm of waking and sleeping. This demonstrates that time perception is not just about clocks, but also about physical signals in the body that quietly guide daily behavior, keeping sleep and wakefulness in balance. Humans often notice a pattern in when they feel sleepy at night. Most people naturally start feeling drowsy around the same hours, even without using a clock. This happens because the body's internal clock, combined with chemical signals and temperature changes, prepares the body for rest at a predictable time. As evening approaches, melatonin levels rise, body temperature drops, and alertness decreases. These signals work together to create a strong sense of sleepiness. The circadian rhythm ensures that these processes occur roughly at the same hours every night. Even in unfamiliar environments, the brain tends to guide sleep toward this natural window. Scientists explain that this regularity helps maintain health, memory, and energy levels. By following a consistent rhythm, the body can rest effectively and recover for the next day. So the reason humans feel sleepy around the same hours each night is not coincidence, but the result of a powerful internal system quietly coordinating multiple signals to guide daily rest. Some people naturally wake up very early, often called early birds, and feel alert in the morning. The reason is connected to the internal clock, or circadian rhythm, inside the brain. In early birds, this rhythm is set so that melatonin begins rising earlier in the evening, encouraging sleep at an earlier hour. As a result, they wake naturally with the sunrise and feel energetic in the first part of the day. Genetic factors also play a role. Scientists discovered that certain genes influence the timing of the circadian rhythm, making some people more likely to wake early or sleep early. Lifestyle and environment can also adjust these tendencies, but the natural rhythm remains strong. Early birds often report feeling tired earlier at night, but their mornings are full of alertness. This pattern has existed for thousands of years, helping humans take advantage of daylight hours for work, hunting, or gathering food, which was crucial in early societies. On the other hand, some people naturally stay awake late at night and feel more active during the evening. These people are often called night owls. Their internal clock is shifted so that melatonin rises later in the evening, making it harder for them to fall asleep early. Because of this, they often feel more awake and alert during late hours, and mornings can feel sluggish. Genetic factors are important here too. Studies show that specific genes influence whether someone is a night owl, affecting the timing of sleep and wakefulness. Social habits, work schedules, and exposure to light can modify the pattern slightly, but the natural tendency often remains strong. Being a night owl is not a choice, but a difference in internal timing. Historically, night owls may have helped societies by staying awake during late hours, keeping watch, or performing tasks when others were asleep, showing that different rhythms can both be useful and natural. Long before clocks existed, early humans still needed to track time for daily activities like farming, hunting, or traveling. One of the simplest and most effective methods they discovered involved observing the sun. During the day, the sun moves steadily across the sky from east to west. By noticing its position at different times, humans could estimate morning, noon, and evening. The length of shadows, the angle of sunlight, and the brightness of the sky became natural indicators of time passing. These observations helped humans plan important activities, like when to plant crops, when to hunt, or when to return home before nightfall. Over generations, humans learned to predict patterns of sunrise and sunset. By using the sun as a guide, they created a reliable and consistent way to measure time without needing complicated tools. This simple method laid the foundation for later inventions like sundials, calendars, and clocks, showing how early observation of nature helped humans organize daily life. Shadows became one of the first simple clocks, offering a visual way to track time. When sunlight falls on an object, it creates a shadow. The shadow's shape and length change as the sun moves across the sky. Early humans noticed that by marking the position of shadows at different times, they could estimate the hour of the day. Some cultures even placed sticks or stones in a line to record shadow positions throughout the day. As the sun moved, the shadow would follow a predictable path. This simple observation allowed humans to divide the day into parts and plan activities with more precision. Unlike modern clocks, shadow tracking relied on careful observation and repeated measurement. It was an effective and practical method for daily life, especially for agriculture and social organization. Using shadows as time indicators shows how humans learn to combine natural phenomena with careful observation to understand the passing of time. Ancient sundials were one of the first tools designed to measure time more precisely than shadows alone. A sundial works by placing a stick, called a gnomon, vertically on a flat surface. As the sun moves across the sky, the shadow cast by the stick changes its position and length. Early humans or civilizations would mark these shadow positions on the ground or on stone surfaces. By observing where the shadow fell, they could estimate the time of day. The sundial relied on predictable solar movement, which repeated daily. It allowed humans to plan activities with more accuracy, such as starting work, performing rituals, or scheduling meetings. Sundials varied in size and design depending on culture and location. Some were small and portable, while others were large and permanent. Although they could not measure minutes like modern clocks, sundials provided a visual and reliable method to track daytime hours. They represent an important step in human understanding of time and its daily organization. Early calendars were often based on the moon, rather than the sun, because the moon's cycles are easy to observe. Each month the moon goes through phases: new moon, first quarter, full moon, and last quarter. These phases repeat in a predictable pattern roughly every 29 and a half days. Ancient civilizations noticed this cycle and used it to mark time. Calendars based on the moon helped people know when to plant crops, hold festivals, or plan journeys. The lunar calendar was especially useful before the invention of precise solar measurement tools. Even today, some cultures and religions continue to follow lunar calendars for holidays and rituals. Tracking the moon allowed early humans to organize life over weeks and months, giving structure to social, agricultural, and spiritual activities. Because the moon's movement is natural and visible every night, it became a dependable guide for measuring longer periods of time beyond just hours in a day. Observing the changing seasons was crucial for early farmers, helping them measure time over the year. They noticed that certain plants grew and produced fruit only during specific months. Temperatures, rainfall, and daylight length changed in regular patterns. By paying attention to these changes, early humans could predict the best time to plant seeds or harvest crops. For example, they would observe when particular flowers bloomed or when specific animals migrated, using these events as natural calendars. The seasons repeat in cycles, making them reliable markers of yearly time. Farmers learned that aligning their work with seasonal changes increased food production and survival. This practical need pushed humans to notice patterns in nature more closely. Observing seasons allowed communities to plan ahead, prepare storage, and manage resources effectively. These early observations laid the foundation for modern understanding of months and years, showing how practical life needs inspired humans to measure and understand time systematically. Ancient civilizations began dividing the day into hours to create a more organized way to track time. They noticed that the day could be broken into smaller, predictable parts. By dividing daylight into equal segments, people could schedule work, religious rituals, and social activities more effectively. Early Egyptians, for example, used shadow lengths and sundials to separate daytime into 12 parts. Nighttime was also divided, often based on the observation of stars or candles burning at a steady rate. Dividing the day into hours made planning easier for both individuals and communities. It allowed different tasks to happen at roughly the same time each day, which improved coordination and social organization. This division of time helped civilizations maintain trade, agriculture, and governance more efficiently. While the length of hours could vary depending on season and daylight, the concept of splitting a day into measurable segments became a standard. It represented an important step toward the precise timekeeping systems we rely on today. Long before modern clocks existed, humans invented water clocks to measure time more reliably than sundials or shadows. A water clock, sometimes called a clepsydra, worked by letting water flow at a steady rate from one container to another. By marking levels on the container, people could track how much time had passed. Some water clocks were simple, while others had intricate designs with floats, wheels, or indicators to show hours. They could measure both day and night, which made them especially useful when the sun was not visible. Civilizations like the Egyptians, Greeks, and Chinese used water clocks for public events, religious ceremonies, and government purposes. Unlike sundials, water clocks worked indoors or during cloudy weather. They were an important step in human understanding of precise time measurement. These early devices showed that humans wanted more accuracy in daily life, planning, and coordination, even thousands of years ago. The steady flow of water became a reliable and visual way to observe time passing, long before mechanical solutions existed. Another simple yet clever method people used to measure time was burning candles. In some cultures, candles were designed with markings along their length to indicate hours. As the candle burned down, the flame slowly moved past these marks, showing how much time had passed. The speed of burning could vary depending on wax, thickness, and wick type, but careful preparation allowed for consistent measurement. Candles were especially useful at night or indoors when sunlight or shadows were not available. People could estimate the passing hours while reading, working, or performing rituals. Some candles were even designed with small weights that would drop when the candle reached a certain point, creating a sound to signal the hour. Using candles to measure time was a practical solution that combined light and measurement in one tool. It helped humans organize work, religious practices, and personal schedules long before mechanical clocks became common, showing the creativity applied to tracking time in daily life. Mechanical clocks gradually transformed society by providing a new, accurate way to measure hours. Early mechanical clocks appeared in Europe around the 14th century, often installed in churches or town halls. These clocks used gears, weights, and escapements to keep time, showing hours and sometimes minutes. Unlike sundials or water clocks, mechanical clocks did not depend on sunlight, water flow, or natural elements. This innovation allowed people to coordinate activities with greater precision, from public events to work schedules. Over time, mechanical clocks became smaller and more widespread, appearing in homes, businesses, and government buildings. Their accuracy and consistency changed how societies planned daily life, trade, and transportation. People could now rely on clocks rather than guessing or observing natural events. This development also influenced science, navigation, and industry, as precise measurement of time became increasingly important. Mechanical clocks marked a major step in human control over time, transforming the rhythm of society and laying the foundation for modern timekeeping systems we use today. Accurate timekeeping became crucial for navigation, especially as humans explored oceans and distant lands. Before precise clocks, sailors could measure latitude using stars and the sun, but determining longitude was much harder. Without knowing exact time, it was almost impossible to calculate a ship's east-west position accurately. Early attempts to solve this problem led to errors and lost voyages. The invention of highly accurate clocks, called marine chronometers, solved this issue. These clocks could keep precise time on a moving ship, even during storms and rough seas. By comparing the local time, determined from the sun, with the time on the chronometer, sailors could calculate their exact position. This breakthrough made long-distance sea travel safer and more reliable. Accurate timekeeping allowed for global trade, exploration, and communication to expand rapidly. It also highlighted how critical precise measurement of time had become beyond daily life, affecting survival, economics, and discovery. Human dependence on accurate clocks became clear, showing that mastering time was essential not just for schedules, but for navigating the entire world. Before the invention of accurate clocks, sailors faced a huge problem when navigating the oceans. They could measure latitude or north-south position by observing the sun or stars, but longitude or east-west position was much harder. Longitude requires knowing the exact time at a reference location, like Greenwich, and comparing it with local time. Without accurate clocks, sailors had no reliable way to tell how far east or west they were. Small errors in time measurement could result in being hundreds of miles off course, causing lost ships or dangerous accidents. This problem made long-distance sea travel risky and limited exploration. People realized that mastering precise timekeeping was not just for schedules but could save lives. The need for exact time at sea created pressure for inventors to develop reliable clocks that could survive rocking ships, temperature changes, and humidity. This challenge was a turning point in human understanding of time, connecting time measurement directly to survival and global exploration. The solution came in the form of precise marine chronometers, invented in the 18th century. These were special clocks designed to keep extremely accurate time on ships, even when the vessel rocked, heated by sun, or cooled by night. Inventors like John Harrison developed chronometers with advanced mechanisms that resisted temperature changes and maintained a steady pace over long journeys. With a marine chronometer on board, sailors could compare local noon, determined by the sun, with the reference time on the chronometer. This comparison allowed them to calculate longitude accurately, pinpointing their exact east-west position. Marine chronometers revolutionized navigation, making sea travel safer and enabling global trade, exploration, and scientific voyages. These clocks were expensive and rare at first, but their success proved the power of precise timekeeping. The invention of the marine chronometer marked a turning point in human history, showing that mastering accurate time could expand the reach of civilization across oceans and continents. In the 19th century, railroads dramatically changed the way humans organized time. Before trains, each town set its own local time based on the sun's position. That worked well when travel was slow, but railroads created a new problem. Trains moved quickly across long distances, and each town having its own time made schedules confusing and dangerous. Trains often ran late or collided because timetables did not match local times. To solve this, countries began to standardize time zones, dividing regions so that all towns in the same zone used the same official time. This allowed train schedules to be consistent, improving safety and efficiency. Standardized time zones spread from railroads to governments, businesses, and schools. By aligning society under a shared clock, humans could coordinate large-scale activities more effectively. Railroads showed that accurate, standardized time was not just a convenience, but a necessity in a world moving faster and covering greater distances than ever before. Before the 1800s, time zones did not exist, and each town or village set its own time based on the sun. Noon was defined as the moment when the sun reached its highest point in the sky locally. This system worked well when most people traveled only short distances on foot or by horse. Communication was slow, and daily activities were organized locally, so there was no need for a uniform time across regions. But with inventions like railroads, telegraphs, and faster transportation, the lack of standardization became a serious problem. People in different towns could be hours apart in their local time, causing confusion for scheduling trains, meetings, and business. The absence of time zones shows how technology and human activity can shape concepts of time. Standardization of time emerged as societies grew more connected and dependent on precision. Before this, time was local, flexible, and mostly observed, not strictly measured or coordinated, highlighting how human needs drive the development of timekeeping systems. As travel, trade, and communication grew in the late 19th and early 20th centuries, the world faced a growing problem. Each country and region had slightly different local times, which made international schedules confusing. To solve this, leaders and scientists worked together to establish a global time standard. In 1884, the International Meridian Conference decided to use the Greenwich Meridian in England as the reference line for 0 degrees longitude. This line, called the prime meridian, became the starting point for calculating all time zones around the world. Countries adopted standard time zones based on their distance east or west from Greenwich. This agreement allowed global coordination for shipping, communication, and finance. It made travel, international business, and scientific research much more predictable. By creating a single reference point for time, humanity established a shared system that everyone could follow. This global standard helped the world become more connected and efficient, showing how human societies gradually unified their understanding of time across continents and oceans. The invention of atomic clocks marked a major leap in timekeeping precision. Unlike traditional clocks that rely on gears, pendulums, or electronic oscillators, Atomic clocks use the natural vibrations of atoms to measure time. Scientists discovered that certain atoms, like cesium or rubidium, oscillate at extremely consistent frequencies. By counting these vibrations, atomic clocks can measure time with astonishing accuracy. Atomic clocks are used to define the official length of a second and to coordinate global systems like GPS, telecommunications, and scientific experiments. Their precision surpasses all previous clocks, making them essential for modern technology. The ability to rely on atomic vibrations allows humans to track time more accurately than ever before. These clocks are not affected by temperature changes, movement, or aging in the way mechanical or electronic clocks are. Atomic clocks represent humanity's attempt to master time measurement at the smallest and most stable scale available. Atomic clocks measure time by tracking the vibrations of individual atoms. Each type of atom has a natural frequency at which it oscillates, like a tiny, precise metronome. For example, cesium atoms vibrate at exactly 9,192,631,770 cycles per second. Atomic clocks detect these vibrations and use them to count seconds with extraordinary consistency. Because the vibration is a property of the atom itself, it does not change with temperature, movement, or age, making it far more reliable than traditional clocks. Engineers and scientists trap atoms in special chambers and expose them to microwaves to measure the frequency accurately. By counting the repeated cycles of these vibrations, the clock creates an extremely steady signal that forms the basis of time measurement. This method allows atomic clocks to define the official second and serve as the standard for international timekeeping. Using the natural rhythm of atoms ensures that time can be measured more precisely than ever before in human history. Atomic clocks are so precise that they lose less than a second over millions of years. This level of accuracy is far beyond anything mechanical or electronic clocks could achieve. The consistency comes from the nature of atomic vibrations, which remain steady regardless of environmental conditions or aging. Engineers carefully shield the atoms from heat, magnetic fields, and other disturbances, allowing the clock to maintain near-perfect timing. Because of this extreme precision, atomic clocks are used to synchronize global systems, including GPS satellites, scientific experiments, and communications networks. Even tiny errors could disrupt navigation or data transmission, so these clocks are essential for modern life. Some of the newest atomic clocks are so stable that they could operate for tens of millions of years without gaining or losing a full second. This shows how humanity has moved from observing shadows and sundials to measuring time at the most fundamental level of matter itself. Atomic clocks truly represent the ultimate mastery of precision in timekeeping. Global Positioning System, or GPS, satellites rely on extremely precise time measurement to work correctly. Each satellite carries atomic clocks that keep time with incredible accuracy, losing less than a second over millions of years. The satellites continuously send signals to Earth, including the exact time the signal was transmitted. Your GPS device, like a phone or navigation system, receives signals from multiple satellites and calculates the distance to each one based on how long the signal took to arrive. Even a tiny error in time, measured in billionths of a second, could result in a location being off by hundreds of meters. Because of atomic clocks in space, GPS can provide precise positioning, navigation, and timing for vehicles, airplanes, ships, and smartphones. Without accurate time, the entire system would fail. This shows that modern technology depends on the mastery of time at its most precise level, connecting atomic measurements with real-world applications across the globe. When you check the clock on your phone, it feels simple and immediate. But the time displayed ultimately depends on atomic time, transmitted through global systems like GPS and internet servers. Your phone's internal clock is just an oscillator, which can slowly lose or gain seconds over days. To stay accurate, phones synchronize with networks that receive time signals from atomic clocks. This ensures your device shows the same precise time that governs global systems, air travel, and scientific measurements. Even though it seems effortless, every second on your phone is linked to vibrations of atoms in distant laboratories and satellites orbiting Earth. Modern life depends on this invisible connection, allowing phones, computers, and networks to communicate efficiently and accurately. Atomic time has moved from laboratories into everyday life, guiding routines, appointments, and digital transactions. It is remarkable to think that the simple act of checking your phone is supported by some of the most precise clocks ever built. In physics, time is considered a dimension, similar to dimensions of space. We often think of space as length, width, and height, describing where something exists. Time adds another axis, showing when something occurs. Without this dimension, events could not be ordered or understood as happening before or after one another. Scientists describe the universe as a four-dimensional system, combining space and time into what is called spacetime. This framework allows for precise predictions of movement, gravity, and cosmic events. Time as a dimension also helps explain why cause and effect work the way they do. Just as you can measure distances in meters, scientists measure durations in seconds, treating time as another coordinate. Considering time as a dimension allows humans to model the universe mathematically, explore relativity, and predict phenomena from falling objects to the orbits of planets. Understanding time as a dimension shows that it is not just a human construct, but a fundamental aspect of the universe. Time is deeply connected with space, forming what physicists call spacetime. Space and time are not separate. Instead, they interact and influence each other. For example, Einstein discovered that massive objects like planets and stars bend spacetime, which affects both the path of objects and the flow of time. Clocks near strong gravity, such as on Earth's surface, tick slightly slower than clocks further away. Similarly, objects moving very fast experience time differently than those at rest. This connection explains why astronauts on high-speed space missions age slightly differently than people on Earth. Understanding the link between space and time has practical applications, including GPS satellites, which must account for both motion and gravity to provide accurate positioning. Space and time form a single fabric, where movement, gravity, and energy all affect the passage of time. This shows that time is not just measured by clocks, but is a flexible part of the universe, intertwined with the very structure of space around us. Spacetime is a concept that combines space and time into a single, four-dimensional fabric. Instead of thinking of space as separate from time, physicists realize that the two are linked and influence each other. Every object, from a tiny particle to a massive planet, exists in spacetime, occupying a specific position in space at a particular moment in time. Events are described not only by where they occur, but also when they occur. Massive objects like planets or stars bend spacetime around them, creating gravity which affects how other objects move. Light, planets, and even time itself follow paths determined by the shape of spacetime. Understanding spacetime allows scientists to predict planetary orbits, the bending of light around stars, and phenomena like black holes. This concept shows that time cannot be considered independently from space. It is part of the structure of the universe, continuously connected with distance, movement, and gravity, forming a flexible framework in which everything exists and moves. Objects in the universe do not just move through space, they also move through time. Even if you are sitting completely still, your body continues traveling forward through time, second by second. Motion in space is combined with motion in time, forming a continuous path called a world line in spacetime. When you walk, run, or drive, you are moving both through space and through time simultaneously. The speed at which you move through space slightly affects how you experience the passage of time, though for everyday speeds, the difference is imperceptible. In physics, this idea explains why astronauts or particles moving very fast experience time differently than stationary observers. Thinking of motion this way helps scientists understand relativity, gravity, and the behavior of objects at high speeds. It also shows that time is not just a backdrop or a ticking clock, but an active dimension that every object travels through, alongside space, continuously, everywhere in the universe. At the basic level, everyone travels through time at the same rate, at least in everyday life. Every human, animal, and object experiences seconds passing at roughly the same pace while on Earth. Your heart beats, your thoughts progress, and events unfold in a shared rhythm with everyone around you. This gives us a common sense of now, allowing humans to coordinate activities, communicate, and live together in society. Even though relativity shows time can change under extreme speeds or gravity, in daily life, the differences are negligible. The shared rate of time is what allows clocks to synchronize, schedules to function, and routines to exist. It is this consistent passage of time that gives life structure. People wake, work, eat, and sleep in a cycle that aligns with everyone else. At this base level, time feels universal and steady, forming the foundation for human perception and organization, before we consider the strange effects of high speed or intense gravity. However, scientific discoveries in the 20th century revealed that time is not perfectly absolute. Albert Einstein's theory of relativity showed that time can stretch or compress depending on speed and gravity. A clock moving very fast or near a massive object ticks more slowly compared to one at rest or far from gravity. This effect, called time dilation, has been confirmed in experiments with satellites, airplanes, and particles moving near light speed. It means that two people experiencing different speeds or gravity can age at slightly different rates. Time is not a fixed, universal backdrop. It is flexible, depending on the conditions of the universe. This discovery changed the way scientists think about time, space, and motion. While it is not noticeable in daily life, it becomes significant in space travel, GPS technology, and high-energy physics. The realization that time is not absolute shows that the universe is far more dynamic and interconnected than we once believed. Motion can actually change the speed at which time passes, a concept that comes from Einstein's theory of relativity. When an object moves very fast, closer to the speed of light, time for that object passes more slowly compared to objects at rest. This does not mean the clock stops, but it ticks at a slightly slower rate. Scientists call this phenomenon time dilation. It occurs because space and time are linked in spacetime, and moving through space affects how you move through time. Even though we do not notice this in everyday life, it becomes significant at very high speeds. Engineers and physicists must consider it when working with satellites, particle accelerators, or space travel. The faster an object moves, the more pronounced the effect becomes. This means that motion is not just a way to change position, but it also influences the fundamental experience of time itself in the universe. Fast movement causes time to slow slightly, but the effect is usually extremely small unless speeds approach light speed. For example, in particle accelerators, subatomic particles moving near the speed of light live longer than they would at rest. Scientists can measure this tiny difference precisely, confirming that motion affects the passage of time. In everyday life, cars, airplanes, and trains move too slowly to notice any measurable effect, so clocks on Earth seem synchronized. However, astronauts and satellites move fast enough that even tiny differences must be accounted for in navigation systems like GPS. The faster something moves, the more time slows for that object relative to a stationary observer. This shows that time is not universal in all situations. It depends on motion. Understanding this helps scientists plan experiments, space missions, and technology that rely on precise timing in a moving world. Astronauts experience time slightly differently because they travel at high speeds and orbit far from Earth's surface. While in orbit, they are moving quickly around the planet, which causes their clocks to run slightly slower than clocks on Earth. Additionally, because they are further from the center of Earth's gravity, the effect of gravitational time dilation also comes into play, though in orbit it slightly offsets the speed effect. As a result, astronauts age just a tiny bit slower than people on Earth. Over a 6-month mission, the difference is usually only a few milliseconds, but it is measurable. This shows that time is not the same everywhere, even within our solar system. Space travel gives a practical demonstration of how motion affects time. Every second in orbit counts a little differently, and modern instruments are precise enough to detect these differences. Human experience combined with advanced technology proves that time is flexible and connected to motion. Gravity also affects time, an effect known as gravitational time dilation. The stronger the gravitational field, the slower time passes relative to areas with weaker gravity. For example, a clock near the surface of Earth ticks slightly slower than a clock far above the planet. This effect becomes extreme near massive objects like stars or black holes, where time can slow dramatically. Gravity warps spacetime, bending both space and time, which means that proximity to mass influences how quickly events occur. GPS satellites must account for this effect, because they orbit far above Earth where gravity is weaker, and their clocks tick faster relative to ground-based clocks. Without adjustments, GPS positioning would quickly become inaccurate. Gravitational effects on time reveal that time is not uniform or absolute. It depends on the environment and conditions. This understanding shows that the universe is dynamic, and time is linked directly to both motion and gravity, shaping how all events unfold. Strong gravity has the power to slow down time, a concept that may seem surprising, but is a fundamental prediction of Einstein's theory of general relativity. Massive objects like planets, stars, or black holes warp the fabric of spacetime around them. This warping affects both space and time, making clocks near these objects tick more slowly than clocks farther away. The stronger the gravitational field, the more pronounced the effect becomes. Near a black hole, time could almost stand still relative to someone far away. Even on Earth, the effect is tiny but measurable. Clocks at sea level tick slightly slower than clocks on mountaintops because gravity is stronger closer to the planet's center. This shows that time is not the same everywhere. Gravity influences it directly. Time is flexible, connected to mass and energy, and cannot be thought of as a simple, universal ticking second. The universe measures time differently depending on where and how massive objects are. Clocks run slower near massive objects because the curvature of spacetime caused by gravity affects the flow of time. The closer a clock is to a heavy mass, the more spacetime bends, and the slower the clock ticks relative to one farther away. This principle applies to planets, stars, and especially black holes. Even though the difference is imperceptible for daily life on Earth, precise instruments can detect it. For example, atomic clocks placed at different altitudes show measurable differences in time. Satellites in orbit experience weaker gravity, so their clocks run faster than those on Earth. Engineers must account for these effects to ensure technologies like GPS remain accurate. The slower ticking near massive objects is not a mechanical problem, but a physical reality of the universe. It demonstrates that time is not absolute. Instead, it is influenced by gravity and mass, which bend spacetime and change the experience of seconds, minutes, and hours for objects in different gravitational environments. Interestingly, scientists predicted these effects of gravity on time long before they could measure them directly. Einstein's theory of general relativity, developed in 1915, suggested that massive objects warp spacetime and affect the passage of time. Using mathematics, he calculated how clocks would tick differently depending on their distance from mass. Predictions included tiny changes on Earth and extreme effects near massive stars or black holes. For decades, these ideas were theoretical because technology was not yet precise enough to detect such small differences. Physicists had to rely on indirect evidence, like the bending of light around the sun, to support the theory. The prediction of time slowing near mass was revolutionary, showing that time is flexible, not fixed. It challenged centuries of thinking that considered time universal and absolute. This ability to predict a subtle effect mathematically before measuring it highlights the power of scientific theory, imagination, and understanding of the universe's hidden rules. Later, experiments confirmed time dilation on Earth, demonstrating that both motion and gravity influence time. In the 1970s, scientists flew highly precise atomic clocks on airplanes around the world and compared them with clocks left on the ground. They observed that clocks in motion experienced tiny delays, matching predictions from Einstein's theory of relativity. Similarly, atomic clocks at different altitudes on Earth showed that those closer to the planet's surface, where gravity is stronger, ticked slightly slower than those at higher elevations. These experiments provided concrete evidence that time is flexible, depending on speed and gravitational field strength. Even small differences, invisible to human perception, could be measured with precise instruments. These confirmations reinforced our understanding of relativity and helped refine technologies like GPS, which must account for both motion and gravity to function accurately. By proving time dilation exists on Earth, scientists showed that the universe operates according to rules far more subtle and fascinating than everyday experiences suggest, revealing the true nature of time. Satellites experience time slightly differently than people on Earth because they are both moving quickly and farther from Earth's gravity. In orbit, a satellite travels at high speed, which slows its clock a tiny bit due to motion, an effect called time dilation. At the same time, it is farther from the center of Earth, where gravity is weaker, so its clock ticks slightly faster compared to clocks on the surface. The two effects work in opposite directions, but the gravitational effect is stronger, making the satellite's clock run a little faster overall. Even though the difference is only a few microseconds per day, it matters for precise systems like GPS, communication satellites, and scientific instruments. Without accounting for this, satellite signals would quickly become inaccurate. This demonstrates that time is not uniform everywhere and that even small changes in gravity or motion can affect the passage of seconds. Time in orbit is subtly different, showing the flexibility of spacetime throughout the universe. Engineers correct these tiny differences in satellite time every day to ensure technology works accurately. GPS satellites, for example, send signals that allow devices to calculate positions precisely. If the onboard clocks ran faster or slower than expected, navigation errors would grow by kilometers each day. To prevent this, engineers program satellites with adjustments that account for both motion and gravitational effects. Ground stations continuously monitor satellite clocks, comparing them to precise atomic clocks on Earth and making corrections as needed. These corrections are calculated in advance using relativity theory, ensuring that signals remain accurate for users on the ground. Without this daily work, smartphones, airplanes, ships, and mapping systems would lose precision quickly. Even tiny fractions of a second matter in technology today. This process demonstrates that modern life depends on understanding the subtle effects of motion and gravity on time, and on applying advanced science to maintain the reliability of systems we rely on every day. Time passes differently across the universe because gravity and motion vary from place to place. Near massive objects, time slows down, while in empty space far from stars or planets, time passes slightly faster. High-speed movement also affects how quickly clocks tick. This means that two observers in different parts of the universe, or moving at different speeds, can experience time at different rates. Even though humans on Earth perceive time as steady, the universe operates according to these rules, making time flexible and relative. Scientists studying distant stars, planets, and galaxies must account for these variations to understand how events unfold. This variability in time also has practical consequences for space travel, satellite communication, and cosmology. Time is not a single, universal rhythm, but a fabric that stretches and contracts depending on conditions. Across the universe, clocks tick differently, showing that time is a dynamic, interconnected part of the cosmos, deeply linked to space, movement, and gravity. Near a black hole, time could slow dramatically due to the extreme gravity present. Black holes have such strong gravitational fields that spacetime curves sharply around them. If you were near the edge of a black hole, called the event horizon, a clock would tick much slower compared to a clock far away in empty space. To a distant observer, it might appear as if events near the black hole are frozen or moving incredibly slowly. This extreme time dilation occurs because gravity bends time itself, not just space. The stronger the gravitational field, the more pronounced the effect. Black holes provide the most dramatic example of time flexibility in the universe, revealing how gravity can alter the passage of seconds, minutes, and hours. Studying these effects helps scientists understand relativity, the behavior of matter under extreme conditions, and the nature of spacetime. Near a black hole, time becomes relative in a way that challenges our everyday experience, showing the universe's most extreme influence on time. A famous example of extreme time dilation occurs near a black hole, where gravity is so intense that time slows dramatically. Scientists and science fiction writers often illustrate this with scenarios where spending just 1 hour close to a black hole could correspond to many years passing for someone far away in space. This happens because the stronger the gravitational field, the slower time ticks for anything within it compared to distant observers. If an astronaut orbited near the edge of a massive black hole, their seconds would feel normal to them. But when they returned, they might find decades or centuries had passed for others. This effect is not just theoretical, it follows directly from Einstein's equations of general relativity. Black holes offer the most extreme examples, demonstrating how flexible and relative time can be. Thinking about 1 hour equaling years stretches human intuition, but highlights the fascinating ways gravity can warp the passage of time across the universe, revealing spacetime's true nature. These extreme effects of gravity and motion on time are not just hypothetical, they are real and measurable. Scientists have observed time dilation using highly precise atomic clocks on Earth, in airplanes, and on satellites. Even tiny differences caused by altitude or speed can be detected and quantified. GPS satellites, for example, require constant adjustments to account for the combination of orbital speed and weaker gravity compared to Earth's surface. Without these corrections, satellite navigation would quickly become inaccurate. Experiments with particles moving at high speeds also show measurable changes in their decay rates, confirming that motion slows time slightly. These observations provide concrete proof that time is not absolute but flexible, influenced by gravity and velocity. Measuring these effects allows technology to function accurately and confirms the predictions of general relativity. The fact that such tiny changes are both measurable and crucial for modern systems shows that time is a real, dynamic property of the universe, not just a human concept. Time seems to move only forward, creating a clear distinction between past, present, and future. Everything we experience unfolds in a sequence, and we perceive events happening in order. This forward flow is fundamental to daily life, memory, and cause and effect relationships. Even though the laws of physics are mostly reversible, our experience of time is asymmetrical. We see eggs break but not unbreak. We remember yesterday but not tomorrow. This apparent direction is called the arrow of time. Entropy, or the tendency of systems to move from order to disorder, helps explain why time appears to have a preferred direction. As the universe evolves, disorder increases and events progress forward. Time's forward movement allows us to plan, learn from experience, and navigate life. Without this perception, life would be chaotic and unpredictable. Understanding why time moves forward remains a key question in physics and philosophy. It shows that while time is flexible, it also has a direction that governs human experience and the unfolding of the universe. One of the most curious questions about time is why we remember the past but not the future. Our brains store memories of events that have already happened, allowing us to learn, make decisions, and create continuity in life. Memories provide a record of cause and effect, helping us predict what might happen next. However, we have no access to the future. Events that haven't occurred cannot yet leave traces in our minds. This asymmetry is connected to the arrow of time, where the past is fixed and the future is open. Physical processes like the increase of entropy support this directionality, making the past distinct from the future. Philosophers and scientists have debated why this happens, but it seems tied to the fundamental structure of the universe. Our perception of time moving forward, combined with memory formation, gives life a sense of continuity and meaning. The inability to remember the future emphasizes that time is not just a sequence of moments, but a one-way journey shaping experience. The arrow of time is a concept used by scientists to explain why time seems to flow in only one direction. Unlike space, which can be traveled freely in any direction, time has a clear forward movement from past to future. This arrow is connected to the way events unfold, the sequence of cause and effect, and how we experience life. It tells us why we grow older, why we remember the past, and why we cannot visit the future. The arrow of time also shows up in physics, especially when studying thermodynamics, the behavior of energy, and the evolution of the universe. It explains why certain processes happen naturally in one direction and not the reverse. Understanding the arrow of time helps humans make sense of daily life, the aging process, and the flow of events in the cosmos. It highlights that while we can move freely through space, time itself has a built-in direction that guides all events around us. Entropy is deeply connected to the direction of time because it measures how disorder changes in a system. In simple terms, entropy tends to increase over time, meaning systems naturally move from order toward disorder. This increase provides a physical reason for the arrow of time, giving it a clear direction from past to future. For example, a tidy room left alone will slowly become messy because small interactions, random movements, and energy changes create more disorder. Similarly, energy spreads out naturally, and organized structures tend to break down unless work is done to maintain them. Entropy is a statistical property of matter and energy, governing how the universe evolves. As entropy increases, time moves forward and events unfold in a predictable sequence. This principle is why clocks tick, ice melts, and stars burn fuel. Entropy links microscopic particle behavior to our large-scale perception of time, showing that the universe has a built-in tendency to progress forward, not backward. Entropy can be understood as the natural tendency of systems to move toward disorder, which is why many processes in nature appear irreversible. When left alone, energy spreads out, materials break down, and structures become less organized. For instance, a sandcastle gradually collapses, a cup of hot coffee cools, and leaves decompose on the ground. All these changes reflect increasing entropy. Entropy is not just about messiness. It is a fundamental law of physics that governs energy and matter. It explains why certain processes happen spontaneously while others require effort. While you can organize a room or repair an object, it requires work to counteract the natural increase in entropy. Over time, the universe itself moves toward higher entropy, with energy becoming more evenly distributed and systems becoming less organized. Entropy is what makes the flow of time noticeable and irreversible. Understanding this tendency helps explain why events have a clear direction and why the arrow of time points steadily forward. Broken things do not naturally reassemble because of entropy, the natural increase of disorder in the universe. When an object is damaged, energy is spread out and the materials move into less organized states. For example, if you drop a glass and it shatters, the shards scatter randomly. The natural laws of physics make it extremely unlikely for those shards to jump back together perfectly on their own. Repairing or restoring something requires work, energy, and careful arrangement, which humans provide. This irreversibility of broken objects illustrates the arrow of time and shows why certain processes are one way. It also demonstrates how microscopic particle movements and energy distributions determine what is possible on a large scale. From spilled liquids to worn-out machinery, entropy explains why order must be actively maintained and why time seems to push everything forward toward disorder. Broken things teach us a practical lesson about time. It moves forward, and the universe prefers chaos unless effort is applied to create order. Heat always flows from hot to cold because energy naturally spreads out from areas of higher temperature to lower temperature. This happens without any external effort, following the basic rules of thermodynamics. When you touch a warm cup of tea, heat moves from the tea to your cooler hand until both reach the same temperature. Ice melts in a drink because the heat from the liquid flows into the colder ice, causing it to warm and change state. This natural movement of energy shows that systems tend toward equilibrium, a more disordered state, which is an example of increasing entropy. The one-way flow of heat gives time a direction because processes move from organized, high-energy states to more random, lower-energy states. Without this pattern, there would be no natural progression or arrow of time. Observing heat flow helps us understand why certain events happen spontaneously and why time seems to move forward, linking energy, disorder, and the passage of seconds in a continuous, measurable way. These patterns of energy spreading and disorder increasing give time its direction in the universe. Because systems naturally move toward equilibrium, with heat flowing from hot to cold and energy dispersing, events happen in a predictable sequence. Entropy increases in every spontaneous process, creating a physical arrow of time that points from the past, when systems were more ordered, to the future, where disorder grows. This directionality is why broken objects remain broken, spilled liquids do not gather themselves, and clocks tick forward rather than backward. The consistent progression of energy and matter toward more probable, less ordered states ensures that the flow of time has a clear orientation. Even though microscopic laws of physics are mostly reversible, these large-scale statistical patterns determine the overall movement of time. By observing these processes, scientists can see why time moves the way it does. Energy flow, entropy, and the universe's tendency toward disorder together shape the forward passage of time that we experience every day. The early universe began in an extremely ordered state, a condition that set the stage for the arrow of time. Right after the Big Bang, energy and matter were concentrated and uniform, with very low entropy. This initial order made the universe highly structured, creating conditions for the formation of atoms, stars, and galaxies. As the universe expanded, entropy began to increase naturally, and systems moved toward more disordered, probable states. This progression from order to disorder provides a physical basis for the forward flow of time. The contrast between the early, highly ordered state and the present, more disordered universe explains why time has a clear direction. Without such an ordered beginning, processes would not unfold in a consistent, measurable sequence, and the arrow of time might not exist. Observing the universe today, from the formation of stars to everyday events, we can trace the influence of that initial order on the passage of time and the evolution of everything around us. Increasing entropy drives the forward flow of time because it creates a natural progression from order to disorder in every system. As energy spreads, materials mix, and systems move toward equilibrium, events follow a predictable sequence that cannot be reversed without external work. This tendency explains why spilled milk does not unspill, why ice melts in a drink, and why broken objects remain broken. In the universe, entropy increases everywhere, from microscopic particle behavior to the motion of galaxies, setting a universal arrow of time. Each moment represents a slightly more disordered state than the one before, and this chain of increasing entropy gives time a direction. Without this progression, the distinction between past and future would be meaningless. The forward flow of time is essentially the manifestation of energy spreading out and systems moving toward more probable, less organized configurations. By observing these patterns, scientists understand why time moves forward and how entropy shapes the sequence of events in the universe. The universe is incredibly old, with scientists estimating its age at about 13.8 billion years. This number is based on observations of cosmic background radiation, the expansion of space, and the formation of galaxies and stars. By studying how light travels across vast distances, astronomers can look back in time, seeing the universe as it existed billions of years ago. Every observation of a distant galaxy or star shows an earlier moment in cosmic history, giving clues about how the universe has evolved. Understanding the age of the universe helps place human history in perspective, showing how tiny our lifespans are compared to cosmic time. It also explains why time and entropy have been steadily increasing for so long, shaping the structure and behavior of matter and energy. By measuring cosmic distances, radiation, and galactic motion, scientists can piece together a timeline of the universe, revealing the incredible journey from the Big Bang to the present moment. Scientists estimate cosmic time using multiple observations and calculations that track the expansion and evolution of the universe. One method involves measuring the rate at which galaxies move away from each other, known as the Hubble constant. By knowing how fast space is expanding, scientists can work backward to estimate when the universe began. Another approach uses the cosmic microwave background, a faint glow left over from the Big Bang, which provides a snapshot of the early universe. Observations of star formation, galaxy clustering, and the abundance of elements like hydrogen and helium also help calculate the universe's age. Combining these methods, scientists arrive at a remarkably consistent estimate of roughly 13.8 billion years. This process requires highly precise measurements, careful calibration, and advanced physics, but it allows us to understand time on a cosmic scale. Estimating cosmic time connects observations from Earth to the evolution of the entire universe, showing how events billions of years ago still influence the cosmos today. Stars act as cosmic clocks because they change in predictable ways over millions or billions of years. By studying a star's brightness, color, and composition, astronomers can determine its age and stage of life. Young stars burn fuel differently than older stars, and patterns of nuclear fusion inside them reveal how long they have been shining. Clusters of stars also provide valuable timing information, as their members formed around the same period. Observing stars at different distances lets scientists see them as they were in the past, effectively looking back in time. These stellar clocks allow researchers to estimate the age of galaxies, trace the formation of elements, and understand how matter evolves over cosmic timescales. Stars give time a measurable, tangible dimension beyond Earth, connecting human understanding to the broader universe. By watching how stars live, age, and die, we can piece together a cosmic timeline that spans billions of years, showing the natural rhythm of time on the grandest scale. Galaxies reveal the history of the universe because their shapes, structures, and motions carry information about past events. Spiral galaxies, elliptical galaxies, and irregular galaxies each tell a story about formation, mergers, and evolution. By observing distant galaxies, astronomers see them as they were millions or even billions of years ago, giving a window into earlier cosmic times. The distribution of galaxies across space shows how matter clumped together after the Big Bang, while their light reveals the chemical elements formed in stars over time. Galaxies also record collisions, starbursts, and other dramatic events, providing evidence of how the universe has grown more complex. Studying these massive systems allows scientists to reconstruct the timeline of cosmic evolution and understand how time has shaped the large-scale structure of the universe. Galaxies are essentially history books written in stars and gas, showing the passage of billions of years and making time visible on a scale far beyond human experience. The universe itself has a timeline, a sequence of events that stretches from the Big Bang to today. By studying light, galaxies, and cosmic radiation, scientists can reconstruct this timeline and see how the universe evolved. Early moments after the Big Bang were dominated by hot, dense energy, gradually cooling as space expanded. Over millions of years, matter clumped together under gravity, forming the first stars and galaxies. This cosmic timeline shows that events unfold in a particular order, from simplicity to increasing complexity. It also illustrates that time on a universal scale is measurable, with distinct phases marked by major transformations. Observing the universe is like looking back through history, with distant light acting as a time machine. Every star, galaxy, and cosmic structure represents a point on this timeline. Understanding the universe's history gives perspective on how time has shaped matter, energy, and the formation of everything we see, revealing a continuous, evolving story that spans billions of years. After the cosmic darkness that followed the Big Bang, the first stars began to form, lighting up the universe for the first time. Initially, the universe was filled with hydrogen and helium gas, spread thinly across space. Gravity pulled these gas clouds together, increasing pressure and temperature until nuclear fusion ignited, creating the first stars. These stars were massive and bright, burning their fuel quickly and producing the first heavy elements like carbon, oxygen, and iron, which are essential for planets and life. This period, sometimes called the cosmic dawn, marked the end of darkness and the beginning of complex structure in the universe. By observing distant stars, astronomers can see them as they were billions of years ago, capturing a glimpse of this early era. The formation of the first stars shows how time allowed matter to organize, evolve, and create the building blocks for everything that would follow, setting the stage for galaxies, planetary systems, and eventually life on Earth. Planetary systems developed later, after the first stars had produced heavier elements through fusion. When massive stars exploded as supernovae, they scattered these elements across space, enriching gas clouds with the materials needed to form planets. Gravity then pulled these enriched clouds together, forming disks of gas and dust around young stars. Within these disks, particles collided and stuck together, gradually building up planets, moons, and other small objects. This process took millions of years, with planets forming at different rates and distances from their stars. Observing distant star systems shows that this process is common throughout the universe. Our solar system is just one example of how stars and planets evolve together. The development of planetary systems illustrates how time allows matter to move from simple gas clouds to complex structures capable of hosting life. It also demonstrates that the universe's timeline is not uniform. Different regions and systems evolve at different speeds, all guided by gravity, chemistry, and the passage of cosmic time. Earth formed billions of years after the universe began, emerging from a solar system that itself took millions of years to develop. About 4.5 billion years ago, a cloud of gas and dust around the young sun coalesced under gravity, forming a molten planet that would become Earth. Over time, collisions with other objects, including a Mars-sized body, shaped the planet, creating its core, mantle, and crust. Water and other elements arrived through impacts, volcanic activity, and chemical reactions, gradually forming oceans and an atmosphere. Life would not appear for another billion years, but the planet was already shaped by cosmic processes. Earth's formation shows that time on a universal scale is immense. Our planet is relatively young compared to stars and galaxies. By studying rocks, isotopes, and planetary structures, scientists can trace Earth's history back to these early events, connecting our world to the broader cosmic timeline. Time on this scale reveals how planets, life, and everything familiar to us are part of a long, unfolding story. A human lifetime is incredibly small when compared to cosmic time, spanning only a tiny fraction of the universe's 13.8 billion year history. Even living 100 years is like a single heartbeat in the grand timeline of stars, galaxies, and cosmic events. Entire civilizations, continents, and species exist for moments that barely register on the universal scale. Yet, even in this brief span, humans witness astonishing changes, observe planets, study stars, and learn about the vastness of space. Our daily experiences, joys, and struggles may feel significant, but they are a fleeting part of a much larger story that stretches across billions of years. This perspective can be humbling, showing that time operates differently at different scales, from microscopic events in cells to the evolution of galaxies. Understanding our small place in cosmic time encourages curiosity, reflection, and awe. Every heartbeat, sunrise, and thought occurs within a universe that has been unfolding for billions of years, reminding us of both our fragility and our connection to something far greater. Every moment we experience is part of that long, unfolding cosmic story, linked to events that happened billions of years ago. The atoms in our bodies were forged in the cores of ancient stars, exploded across space, and eventually became part of Earth. Every breath, heartbeat, and thought depends on these processes, connecting our present to the distant past. Even the passage of seconds on a clock reflects energy moving, particles interacting, and physical laws at work, all rooted in the history of the universe. Our lives, though short, continue the story of matter and energy evolving over billions of years. By paying attention to each moment, we can feel connected to this immense timeline. The seemingly ordinary passage of time becomes extraordinary when seen as a continuation of cosmic events, showing that even fleeting human experiences are woven into the universe's vast, ongoing history, linking us to every star, planet, and galaxy. Returning to the everyday experience of time, we notice seconds passing, mornings turning into nights, and days flowing into weeks. While cosmic events happen on scales far beyond human comprehension, our perception of time is shaped by rhythms we can observe, like heartbeats, seasons, and clocks. Each moment feels real, measurable, and meaningful, even though it is only a tiny part of the universe's long story. We experience time in a linear way, seeing the past in memories and the future as possibilities. Our brains interpret signals, movement, and change to make sense of the passage of seconds. Daily routines, social interactions, and personal milestones create a structure for understanding our lives within the broader context of time. Observing time this way helps us plan, learn, and grow. While the universe's timeline is immense, the flow of seconds on Earth gives life rhythm and meaning. Every ordinary moment, though small, connects to a vast cosmic framework that stretches across billions of years. Every second we experience is the result of countless cosmic events, from nuclear fusion in distant stars to chemical reactions within our bodies. The energy powering our planet comes from the sun, a star formed billions of years ago, while the atoms in our bodies were created in earlier stars. Gravity shapes planetary orbits, light travels across vast distances, and energy flows through ecosystems, all contributing to the passage of time we perceive. Even the ticking of a clock relies on electrons moving and vibrations in atoms, phenomena governed by universal laws. This means that each moment is not isolated, but part of a complex web of cause and effect spanning space and time. Time, at its core, is the unfolding of countless interactions, both visible and invisible. Recognizing this can make every second feel richer, as we understand it is built upon the history of the universe, connecting our lives to stars, galaxies, and the fundamental processes that have shaped existence for billions of years. Time connects everything in the universe, linking stars, planets, humans, and even the tiniest particles into a continuous, unfolding story. Every movement, every interaction, and every event is part of this grand timeline. Light from distant galaxies reaches Earth after billions of years, carrying information about the past. The atoms in our bodies were forged in the hearts of ancient stars, meaning we are literally made of the universe. Even events on Earth, like weather patterns, volcanic eruptions, and ocean currents, are tied to cosmic forces and cycles. Time allows cause and effect to operate, creating structure in the universe and making it possible to understand history and predict future events. Thinking about time this way transforms the ordinary into something extraordinary. Every action and every moment is connected to a vast web of cause and consequence that stretches across space and time. Time is not just a measure but a binding thread, uniting all things in the universe. Even ordinary moments belong to this vast timeline, linking the present to the distant past and the future that has yet to unfold. Simple experiences, like watching a sunset, having a conversation, or feeling the warmth of the sun, are part of the continuous flow of time shaped by cosmic and earthly events. The air you breathe, the light you see, and the atoms in your body all have histories that stretch billions of years. By understanding that each ordinary moment is embedded in this larger timeline, we gain a sense of connection to the universe and to the countless events that make life possible. Small daily actions, though seemingly insignificant, are woven into the ongoing story of energy, matter, and time. Recognizing this can make life feel more meaningful and grounding. Every second, every thought, and every movement is a link in the chain of the universe, connecting us to the cosmic story unfolding all around us. As night approaches, the body naturally slows down, following an internal rhythm tuned to the day-night cycle. Hormones like melatonin are released, signaling that it is time to rest and recover. Heart rate decreases, muscles relax, and the mind shifts from alert activity to calm awareness. This natural slowdown helps prepare the body for sleep, giving time a tangible effect on our physiology. The cycle of waking and sleeping is part of the circadian rhythm, a built-in clock that keeps humans synchronized with Earth's rotation and the changing light. This rhythm ensures that the body functions optimally, with energy and alertness rising during the day and decreasing at night. By noticing these changes, we can align our activities with the natural flow of time. The approach of night, combined with the body's internal signals, creates a quiet, steady transition that connects our daily experience to the larger cycles of time in nature and the universe. The quiet rhythm of breathing offers a simple, constant reminder of the passage of time. Each inhale and exhale marks a moment, a small cycle that reflects the body's interaction with the world. Breathing connects us to life itself, providing oxygen for cells, removing waste, and supporting every process in the body. When we focus on the gentle rise and fall of our chest, we can become more aware of time flowing in a subtle, tangible way. This rhythm mirrors other natural cycles, like the day-night transition, heartbeats, and planetary rotations, creating a continuous pattern of movement and rest. By paying attention to our breathing, we can feel time moving through us in the present moment, linking our personal experience to universal processes. Each breath is both ordinary and extraordinary, a small pulse in the vast timeline of life. Time, in this way, is experienced intimately, connecting the body, mind, and universe in a quiet, steady rhythm. Time continues even while we sleep, moving steadily whether we are awake or at rest. While our minds and bodies recharge, the universe keeps unfolding. Stars rotate, planets orbit, and atoms interact in endless cycles. Sleep does not stop the passage of seconds, minutes, or hours. Rather, it allows us to align with natural rhythms, restoring energy for the day ahead. The body and brain remain active at a subtle level, repairing cells, consolidating memories, and regulating hormones, all synchronized with the flow of time. Nighttime is not a pause but a quieter part of the day's ongoing journey. Even when consciousness fades, the world continues its rhythm, with tides, weather, and cosmic events marching forward. Recognizing this helps us trust that time will carry on without effort, and that resting is a natural part of life. Sleep is simply a gentle chapter in the ongoing story of existence, one moment in the infinite continuity of time. Sleep can be seen as another peaceful chapter in the flow of time, a period where the body and mind are engaged in quiet, essential work. During sleep, the brain processes experiences, sorts memories, and repairs connections, while the body restores energy and strengthens systems that keep us alive. This phase is part of the natural daily rhythm, as predictable and essential as sunrise and sunset. Sleep allows us to move through time in a slower, gentler way, creating balance and preparing us for the next waking period. Just as the universe continues its enormous cycles, our bodies continue theirs on a smaller, intimate scale. Accepting sleep as a necessary and restorative part of the day reminds us that time encompasses both activity and rest. It is not wasted, but integrated into life's ongoing flow. In this way, sleep is a natural chapter, quietly advancing time while nurturing the body and mind. Tomorrow will arrive naturally, without effort, following the steady flow of time. No action is needed to make the next day come. It is guaranteed by the continuous passage of seconds, minutes, and hours. The universe moves forward, and our lives move with it, carrying the promise of new experiences, opportunities, and moments. This natural unfolding allows us to release worry or urgency about what is coming, trusting that the flow of time will bring the next chapter exactly as it should. Every sunrise is a sign that time continues, independent of human control, yet always providing the context in which our lives unfold. Recognizing this gives a sense of peace, reducing stress about the future. Each moment leads to the next, and tomorrow is simply the next link in the unbroken chain of time. By understanding this, we can live fully in the present while knowing the future will arrive naturally and inevitably. While time never stops, it is perfectly okay for now to simply rest. The universe continues its vast, intricate motion, and yet each person can pause, breathe, and be present in the quiet of this moment. Rest is part of life's rhythm, as necessary as activity, growth, and change. Even as seconds tick by, allowing the body to relax and the mind to settle contributes to the ongoing flow of existence. Sleep, stillness, and reflection are not interruptions. They are essential chapters in the story of time, helping us move through life with balance and energy. Accepting rest without guilt is a way to align with the natural order, recognizing that life will continue regardless. In this quiet pause, you are connected to the larger rhythm of the universe. Time will continue, planets will orbit, stars will shine, and for now it is enough to simply be, breathe, and rest peacefully.